By the 14th century, northern Italy had become one of the richest regions in Europe. The Genoese and Venetian trade superpowers of the Mediterranean brought untold wealth from across Europe and Asia into the Italian peninsula. However, this was not to last. The beginning of the Little Ice Age, a period of unusually colder weather throughout the North Atlantic, resulted in agricultural decline and famines. The devastating Hundred Years' War and the gradual decline of trade from the East because of Ottoman expansion contributed to the hardship. If European peasants thought this was bad, the seemingly apocalyptic dance macabre of the Black Death resulted in the loss of a third of Europe's population. The labor shortage that came afterwards led to higher wages and increased wealth among the population. As the plague subsided, Europe's population grew, creating a demand for goods and services and fostering the rise of bankers, merchants, and artisans. This contributed to the emergence of the Italian Renaissance in the 15th and 16th centuries. The Renaissance saw a revival of the concept of humanism, which emphasized the significance of individualism, human morals, secularism, and a keen curiosity about the world. Scholars, many of whom fled Constantinople following its conquest by the Ottomans in 1453, were motivated by ancient Greek and Roman writings to challenge old conceptions and study the natural world via actual empirical observation and critical thought. Renaissance concepts inspired men such as Martin Luther, Jan Hus, and John Calvin to launch the Protestant Reformation in 1517. Their demands for reform in the Catholic Church, notably those of Martin Luther, called into question the authority of the Church. The Protestant Reformation destroyed religious unity in Europe, but established an atmosphere of inquiry, critical analysis, and receptivity to new ideas. The challenge to old religious dogmas paved the way for the challenge to other established ideas, including those in the world of science. On February 19, 1473, Nicolaus Copernicus was born in Poland. Copernicus studied liberal arts, including astronomy and astrology, at the University of Krakow, before continuing his studies in Italy at the University of Bologna. During his time in Bologna, he was introduced to influential books that shaped his understanding of astronomy and astrology. He made numerous observations throughout his life, focusing on eclipses and celestial alignments. In the late 15th century, planetary motion, their position in the stars, and astrology were subjects of debate. These debates were based on two geocentric models, the idea that the solar system and the universe orbits around the Earth. The ancient Aristotelian tradition held that the planets are carried and move around the center of the universe embedded in unchangeable, material, invisible spheres at fixed distances. Claudius Ptolemy improved upon this by introducing the idea of uniformly revolving, off-center circles whose centers moved uniformly on the circumference of circles of a larger radius. In his book Commentariolus, Copernicus proposed an orderly arrangement of the solar system's planets based on a motionless sun and a moving Earth, a heliocentric model in which the solar system orbits around the sun. However, this theory raised challenges. It abandoned the traditional and natural Aristotelian philosophy. In 1543, Copernicus finalized his theories and findings about the heliocentric model in his book De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres. Despite unauthorized revisions made by the theologian Andreas Osiander in preparation for its publication, De Revolutionibus and Copernicus was successful in his goal of debunking the geocentric model. His findings flew in the face of the contemporary orthodox views of Aristotle's and Ptolemy's geocentric views, views that, like Martin Luther, challenged the views upheld by the Roman Catholic Church. Copernicus's findings, unbeknownst to him or his contemporaries, kick-started the scientific revolution, spurring a slew of new discoveries in astronomy, physics, chemistry, and anatomy by European scholars. However, his new heliocentric model was not unique in heliocentric theory, as many others came before him, notably Aristarchus of Samos. In the 3rd century BCE, the Greek astronomer Aristarchus of Samos proposed a heliocentric model of the universe. His work, however, did not gain significant recognition during his time. Aristarchus's heliocentric hypothesis challenged the prevailing geocentric model endorsed by Aristotle. Despite its intellectual merit, Aristarchus's radical proposal faced resistance and was overshadowed by the dominance of geocentrism. Many others, especially the Muslim scholars of the Islamic Golden Age, like Ibn al-Haytham and the Maragha school, attempted to challenge and criticize the geocentric model by developing non-Ptolemaic models of their own. However, much like Aristarchus, their findings did not catch on as quickly and as widely as Copernicus's. So this begs the question, why didn't the scientific revolution happen earlier? In both the world of antiquity and medieval Europe, the geocentric model aligned with religious doctrines and societal worldviews. The heliocentric ideas challenged long-established beliefs and faced resistance from religious authorities who considered them heretical. However, with the Protestant Reformation and its encouragement for the independent interpretation of texts, challenging Rome's authority and its focus on actual evidence, the scientific revolution and Copernicus's findings were allowed to spread as they did when they did. The dissemination and communication of scientific ideas were limited during earlier periods. The works of Aristarchus and al-Haytham had limited circulation and reach, hindering their impact on the wider scientific community. Copernicus, however, had the benefit of Johannes Gutenberg's printing press, invented in 1440, allowing for the mass production and spread of ideas through books and paper productions, thus allowing for the exchange of knowledge necessary for a scientific revolution. Copernican astronomy, the revolutionary scientific framework developed by Nicolaus Copernicus in the 16th century, faced initial opposition but eventually gained widespread acceptance through a process of infiltration. Initially, professional astronomers largely ignored Copernicus's book De Revolutionibus. However, they recognized the value of the mathematical techniques employed in the book, leading to its widespread adoption as a standard reference among the astronomical community. One crucial development that contributed to the acceptance of Copernican astronomy was the publication of the Prutenic Tables, or the Prussian Tables, by Erasmus Reinhold. These tables, based on Copernican methods, provided highly accurate predictions of celestial positions and became indispensable tools for astronomers and astrologers alike. As a result, many professionals began incorporating Copernican principles into their work, embracing certain aspects of the new system. The observational advancements made by the Danish astronomer Tycho Brahe further bolstered the credibility of Copernican astronomy. His observation of a new star and comets in the supposedly unchanging heavens further undermined the Aristotelian view. Brahe's data provided compelling evidence supporting the dynamic nature of the universe and aligning with the Copernican model. In the early 17th century, the German astronomer Johannes Kepler, building upon Tycho Brahe's data, solidified the Copernican hypothesis by formulating two fundamental laws of planetary motion. Kepler's first law described the elliptical orbits of planets, deviating from the traditional belief in circular motion. His second law, known as the law of equal areas, revealed that a planet sweeps out equal areas in equal time intervals as it moves along its elliptical path. These laws provided a mathematical foundation for the Copernican model, further strengthening its acceptance within the scientific community. Galileo Galilei, a prominent Italian astronomer and physicist of the 17th century, played a pivotal role in dismantling traditional cosmological beliefs through his groundbreaking observations with the telescope. Galileo's discoveries included the rough and imperfect surface of the moon, the phenomenon of earthshine, the faint illumination of the moon's dark side caused by sunlight reflected off the Earth, the presence of 4 satellites orbiting Jupiter, now known as the Galilean moons of Io, Callisto, Europa, and Ganymede, as well as the phases of Venus. These observations, as well as his work Dialogue concerning the 2 chief world systems, directly supported the heliocentric model proposed by Copernicus and refuted the geocentric worldview advocated by the Catholic Church at the time. Because of his views, however, the Catholic Church declared him to be a heretic and forced him to recant, or in other words, say that his works and findings were not legitimate. The battle between Copernican heliocentrism and Ptolemaic Aristotelian geocentrism extended beyond astronomy and bled into the realm of physics. The traditional system relied on Earth being at the center of the cosmos, and any shift from this notion undermined the principles of natural motion and circular motion according to Aristotelian physics. Galileo's ideas about motion and the universe were closely linked to his support of Copernicus's theory that the Earth revolves around the Sun. At first, he followed the traditional understanding of how objects move, but he eventually developed a new understanding that supported the idea of heliocentric cosmology. Galileo's investigations focused on how objects fall. This led him to formulate the law of free fall, which says that the characteristics of an object, like mass and shape, don't affect how it falls in a vacuum. Using this idea and his basic principle of inertia, which states that objects in motion tend to stay in motion, Galileo was able to explain the curved path of objects like projectiles. He found that objects follow a parabolic trajectory when they are thrown or shot through the air. Galileo's principle of inertia also helped him counter arguments against the Earth's motion. He reasoned that if the Earth were truly moving, then objects on its surface would also be in motion. However, because of inertia, this motion is not easily noticeable to people on Earth. René Descartes, a 17th-century French philosopher, focused on foundational problems in science, including matter and motion. His mechanical philosophy aimed to explain all natural phenomena in terms of matter and motion. Descartes rejected the idea of empty space and proposed that forces are propagated by an ether substance filling all space. He believed that matter moves in straight lines according to the principle of inertia, but cannot occupy space already occupied by other matter, resulting in vortex-like motion. Sir Isaac Newton's work in the late 17th century, however, marked the culmination of the scientific revolution. His book, Philosophiae Naturalis Principia Mathematica, solved major problems in mechanics and cosmology, providing a physical basis for Kepler's laws and unifying celestial and terrestrial physics. Newton's concept of force synthesized the mechanical philosophy and the mathematization of nature. Newton's 3 laws of motion formed the basis for his findings. Newton's first law: a body remains at rest or in uniform motion in a straight line unless acted upon by an external force. Newton's second law: the rate of change of motion is directly proportional to the applied force and occurs in the direction of that force. Newton's third law: for every action there is an equal and opposite reaction. The second law was later expressed as F equals ma, with acceleration, represented by A, being directly proportional to the force, represented by F, and inversely proportional to mass, represented by M. Newton used Descartes' ideas about how things move to explain how objects in space move. He said there is a force of gravity between any 2 objects in the universe, even though he didn't know exactly how it worked. By using his laws of motion and the idea that gravity gets weaker as objects get farther apart, Newton figured out the 3 laws that describe how planets move around the sun. He also showed that Galileo's idea about objects falling on Earth was consistent with his laws. The same force that makes things fall on Earth also keeps the moon and planets in their orbits. Newton's ideas also showed that Earth is not a perfect sphere, but bulges out at the equator. French expeditions in the 1700s confirmed this, and it convinced scientists in Europe to stop using Descartes' ideas and start using Newton's ideas instead. Newton also explained why the axis of Earth's rotation changes direction over time, using Earth's bulging shape, and how the moon and sun affect it. The realm of optics and lights has been a fundamental part of science and went under a dramatic change with the scientific revolution. The study of optics started in ancient Greece, with Euclid discovering geometric optics, including the law of reflection. In the 13th century, people like Roger Bacon and Robert Grosseteste studied optics, building on the work of Ibn al-Haytham. Issac Newton made significant contributions to optics, especially in his theory of colors. Traditional theory considered colors to be the result of the modification of white light. Newton, however, demonstrated that white light can be separated into different colored lights, or spectrums, using prisms. Newton's approach to experiments involved quantifying variables and distinguishing between experimental findings and mechanical explanations. He also investigated interference phenomena, such as Newton's rings, which involved observing the relation between the thickness of thin films and the diameters of color rings. Chemistry became its own separate science in the 17th century thanks to the rise of mechanical philosophy. Aristotle believed that everything was made up of 4 elements: earth, water, air, and fire. These elements could change into one another and were present in all things. Alchemy, on the other hand, was a practical pursuit that aimed to turn ordinary substances into gold. Alchemy brought a long tradition of working with different substances into the field of chemistry. In the 16th century, Paracelsus, a Swiss natural philosopher, combined Aristotle's ideas about matter with alchemical correspondences, mystical knowledge, and chemical therapy in medicine. By the first half of the 17th century, there were no widely accepted ideas or doctrines in chemistry. As a result, not much knowledge had been accumulated. Chemists tried to create detailed systems called chemical philosophies to explain the entire universe using chemistry. Many chemists believed in the traditional 4 elements or the Paracelsian principles of salt, sulfur, and mercury as the true qualities of substances. The relationship between chemistry and Descartes' mechanical philosophy changed this situation by giving chemists a common language. The mechanical philosophy had already been successful in other areas and seemed to align with experimental observations. This made chemistry more respected by translating it into the language of the new science. Robert Boyle's work is a good example of the influence of mechanical philosophy. He aimed to understand the chemical properties of matter, provide experimental evidence for the mechanical philosophy, and demonstrate that all chemical properties can be explained using mechanical terms. During the scientific revolution, astronomy and physics made significant progress, while medical science and biology advanced at a slower pace. Prevailing beliefs and biases hindered extensive experimentation, particularly regarding human cadavers. Most doctors relied on the ancient theories of Galen, who proposed the existence of 4 humors that governed health: blood, phlegm, yellow bile, and black bile. Illness was believed to result from an imbalance of these humors, leading to the practice of bleeding patients to reduce excess blood. Despite the continued influence of humor theory, progress was made in anatomy. Italian Dr. Andreas Vesalius published an anatomical work based on cadavers, and William Harvey demonstrated that blood circulates through the body, pumped by the heart rather than originating from the liver as previously believed. Microscopes, a new invention starting in 1590, were later used to detect capillaries connecting arteries to other tissues. This growing understanding of the human body aligned with the concept of it being part of the natural world. However, this newfound knowledge of anatomy did not immediately lead to an understanding of contagion. It wasn't until the 1860s, with the work of Louis Pasteur, that definitive proof of the relationship between germs and sickness was established, called germ theory. The scientific revolution in Europe brought about a radical transformation in human understanding of the natural world. At the heart of this intellectual upheaval was empiricism, a philosophical framework that emphasized the primacy of first-hand experience and direct observation. Before the scientific revolution, scientific knowledge was largely confined within the realm of ancient authorities, particularly the ancient Greek philosopher Aristotle and his followers. The Aristotelian and scholastic philosophies dominated intellectual thought in ancient and medieval Europe, emphasizing deductive reasoning, the idea that if the premises are true, then the conclusion must be true, as well as reliance on established dogmas and deference to authority. Science was considered an abstract pursuit rather than an empirical endeavor. In medieval Western Europe, the Catholic Pope reigned supreme, even above kings and emperors. Strict adherence to the Bible as per the papacy's word, and ideas such as creationism, the belief that God made the world, stifled scientific progress for centuries. According to the papacy, geocentrism was the reality. This dogma led to incidents like those that Galileo faced. However, the Protestant Reformation, the exploration of the New World, the invention of the printing press, and the dissemination of ancient texts triggered a paradigm shift. Francis Bacon, an inspiration of the scientific revolution, advocated for a new approach to acquiring knowledge. His influential work, Novum Organum, promoted the use of systematic observations and experimentation as the foundation of scientific understanding. Bacon called for the rejection of dogma, encouraging scientists to question prevailing beliefs and rely on empirical evidence. People should base their facts on evidence and observation made by others as well as by themselves, and not off on what a supreme authority told them. While not an outright empiricist, René Descartes sought to establish a secure foundation for knowledge through a methodological approach centered around skepticism. He emphasized the use of reason to discover truth, but his ideas on mathematical deduction opened new avenues for empirical investigation. Galileo Galilei challenged traditional notions of the cosmos through his groundbreaking empirical observations. By utilizing the telescope, Galileo discovered celestial bodies that undermined the geocentric model of the universe. His experiments and meticulous record-keeping set a new standard for empirical verification, undermining blind acceptance of ancient authorities. Isaac Newton epitomized the empirical spirit through his monumental work, Principia Mathematica. Newton's laws of motion and universal gravitation were derived from meticulous observations and mathematical formulations. By grounding his theories in empirical evidence, Newton established a framework for understanding the physical world, revolutionizing the study of physics. Empiricism served as the catalyst for scientific progress during the scientific revolution, liberating scientific inquiry from the shackles of tradition and dogma. By demanding empirical evidence and fostering a spirit of skepticism, this approach laid the foundation for modern scientific methods. Its influence extended beyond the realms of natural philosophy, permeating fields such as medicine, chemistry, and biology.